This is Shakil Ahmed. In this tutorial, we will discuss about gradient boosting algorithm for prediction problem. Gradient boosting algorithm is a most powerful machine learning algorithm that is used for both regression and classification problem. It's just like decision trees, but it works sequentially instead of growing trees in parallel like random forest. So the gradient in gradient boosting comes from the fact that it uses a gradient descent algorithm to minimize the loss function. At each step, the algorithm fits a new tree to a negative gradient of the loss function, which essentially means it tries to find the direct direction of steepest descent, basically the minimum loss, and then find prediction as the weighted sum of all the predictions obtained from the individual trees. So it builds trees one at a time, where each new tree helps to correct error model by previous trained tree, and it combines the number of weak learners and provide a stronger learner, and then it also less prone to overfitting as the decision tree, the random forest. So we will implement the gradient boosting algorithm to predict the chronic heart disease status using different clinical and demographic characteristics in this data set. This is the Framingham data set I have downloaded from Kaggle. The Kaggle link is also available here. I can share this link in the comments if you need. So I have just uploaded this data and run the data set. Now the data set is here. First of all, we need to check for any missing values in the variables, in the predictors, and in the outcome variable. So we will just check if there is any missing values. So we have 105 missing values in education, and the uh, cigarette number of cigarettes per day, and then blood pressure and other certain variables. So what we will do, we will remove the missing values, missing the cases where the missing value is in this response variable, just using the remove option, drop NA, then subset only I am taking this variable, and then in place is equal to true. It will drop out all the NAs uh, in the chronic heart disease. So you can just do this. Then we will column the quantitative. We will separate the columns into quantitatives and qualitative based on the variable type, data type, float, and then integer 64. And this is basically used for the uh, quantitative variables, and this is for qualitative variables. So we just separated the data columns into two types, and then we impute the missing values in columns, in the quantitative columns with the mean, and the qualitative columns with the mode of the that column with available cases. We just take the mean of the available cases and then replace it with the missing values, and in case of qualitative, we will replace with the mode. But it is not a good idea in practical situations to replace the missing values with modes, or even in by means. You need to apply certain machine learning algorithms to predict the missing values first by using the available data set, and then you can replace predict the missing cases by other available values in other variables. You can just take the variable with missing value as the response variable and train a model, uh, and then predict the the missing cases using the just considering as the test set. So you can do that, but for simplicity, we are just replacing the mean by the quantitative variable, missing value variables, missing values in the quantitative variables, and the missing values in the qualitative variables are replaced by the mode. And then we can see if there is a missing values in the variable. So now we have no missing values in any of the variables selected in the analysis. So we will just select the data frame, all the variables as axis, but just removing the chronic heart disease status, the response variable from the data set, and taking all other variables like all these variables, just removing this. We will keep all other variable as the predictors, and this is the response variable, and we will uh, split the data into test and training with 20% in test. This is the test site, and this is random start to select the to split the data in randomly in test and training. And then we can see the number of observations in these two. You can just find the extract data dot shape to see the shape of the data set. So we have this much observations and this much uh, variables in the x data frame, and y is just a vector consisting this number of observation. It has only one column. So we will run this, and then we need to train our model from sklearn ensemble. This comes into the ensembling methods. So sklearn ensemble, and then import gradient boost classifier, and then we just name it as GBC gradient boost classifier with random start this, and then we will give the we will fit the GBC fit using GBC fit, and inputs are X train and Y train. So this will train your model on X train and Y train, and then we can predict using the GBC dot predict using the X test, means the predictors for test set, and then we get the predictors for uh, uh, Y predicted for the test set, and we can see, for example, first 100 observations for Y predicted. So we have a few, only 3 cases with chronic heart disease predicted in our predictive data. And then we will see we need to evaluate the performance of the model using the different performance measures. If you want to tune your hyperparameter using for example what should be the learning rate and other things, you can set them using um, hyperparameter tuning method. I have skipped this to avoid complexity in the tutorial, so as it is a basic tutorial. So now we need sklearn metric. From sklearn metrics we need these performance measures as we did in previous uh, tutorials, and then from Seaborn we need SNS, and from Matplot library we need PLT to see the to make the visualization plots. So I will run this, and then the performance matrix accuracy underscore score, and then Y test and Y training, then precision score, and then recall score, and then F1 score. So I will get all these. The accuracy is 84%, and the precision is 34%, and recall is only 6%, and F1 score is almost 0.1, 0.2, 0.11, you can say. And we will just visualize this in terms of confusion matrix. This is the number of true, false positive, and true negative, and this is true positive. These are basically predicted as one, and actually they were as reported as one. So So accuracy is just the sum of these two and divide by total number of observation. And we can also see the precision and recall uh, to see the model performance, but mostly used measure is accuracy, and then sometime we compare the different models using the F1 score. So this is the model which provide a the confusion matrix provide a detail about these two on these observations in our data set. How many predicted as true uh, actual disease and predicted as diseased, and how many were non-diseased and predicted as non-diseased. So this is the important visualization of the prediction performance of our model. And then in most of the uh, real world scenario, we need to check the variable importance, which variable is more important in predicting the outcome. So we will just find the variable importance plot using the feature importance PD series, and then the GBC dot feature importance. This is just within the GBC object we have uh, we just ground here GBC. So just like GBC fit, we need to GBC dot feature importance, and then index as X train columns. Within training data, we just take the X train columns, and then we will sort the feature importance as sort values ascending order. So then we will make a plot for this. On x-axis we have feature importance, and y-axis we have feature importance values, and then we can just plot this so you can see this is the importance values and these are the features. So you can see age is most important variable in our data set, followed by systolic blood pressure, glucose, and diastolic blood pressure, and education, and current smoker and diabetes status are least important variables in predicting heart disease, chronic heart disease. So that's all about the gradient boosting algorithm. It is uh, more interesting to see that gradient boosting is a machine learning technique that builds a strong predictor model by sequentially combining a series of weak model, typically decision trees. So we got a higher accuracy of 84.67%, and this is just an alternate of random forest and even logistic regression, and it is a most powerful statistical learning model. Thank you.